common expression, solid as a rock, suggests something that is hard or unyielding and has a definite shape and volume. In this section, we will examine the properties of solids and compare them with those of liquids and gases. The properties of solids are explained in terms of the kinetic molecular theory, as are the other states of matter. First, main idea. The particles in a solid hold relatively fixed positions. The particles of a solid are more closely packed than those of a liquid or gas. Intermolecular forces, IMFs, between particles are thus much more effective in solids. All interparticle attractions, such as dipole-dipole attractions, London dispersion forces, and hydrogen bonding, exert stronger effects in solids than in the corresponding liquids or gases. Attractive forces tend to hold the particles of a solid in relatively fixed positions, with only vibrational movement around fixed points. Because the motion of the particles are restricted in this way, solids are more ordered than liquids and are much more ordered than gases. The importance of order and disorder in physical and chemical changes will be discussed in a different chapter. There are two types of solids: crystalline solids and amorphous solids. Most solids are crystalline solids. They consist of crystals. A crystal is a substance in which the particles are arranged in an orderly, geometric, repeating pattern. Non-crystalline solids, including glass and plastics, are called amorphous solids. An amorphous solid is one in which the particles are arranged randomly. The two types of solids will be discussed in more detail later in this section. Definite shape and volume. Unlike liquids and gases, solids can maintain a definite shape without a container. In addition, crystalline solids are geometrically regular. Even the fragments of a shattered crystalline solid have distinct geometric shapes that reflect their internal structure. Amorphous solids maintain a definite shape, but they do not have the distinct geometric shapes of the crystalline solids. For example, glass can be molded into any shape. If glass is shattered, the fragments can have a variety of irregular shapes. The volume of a solid changes only slightly with a change in temperature or pressure. Solids have definite volume because their particles are packed closely together. There is very little empty space into which the particles can be compressed. Crystalline solids generally do not flow because their particles are held in relatively fixed positions. Definite melting point. Melting is the physical change of a solid to a liquid by the addition of energy as heat. The temperature at which a solid becomes a liquid is its melting point. At this temperature, the kinetic energies of the particles within the solid overcome the attractive forces holding them together. The particles can then break out of their positions in the crystalline solids, which have definite melting points. In contrast, amorphous solids, such as glass and plastics, have no definite melting point. They have the ability to flow over a range of temperatures. Therefore, amorphous solids are sometimes classified as supercooled liquids, which are substances that retain certain liquid properties even at temperatures at which they appear to be solid. These properties exist because the particles in an amorphous solid are arranged randomly, much like the particles in a liquid. Unlike the particles in a true liquid, however, the particles in amorphous solids are not constantly changing their positions. High density and incompressibility. In general, substances are more dense in the solid state. Solids tend to be slightly denser than liquids and much denser than gases. The higher density results from the fact that the particles of a solid are more closely packed than those of a liquid or gas. Solid hydrogen is the least dense solid. Its density is about 1/320th that of the densest element, osmium, represented by OS. Solids are generally less compressible than liquids. For practical purposes, solids can be considered incompressible. Some solids, such as wood or cork, may seem compressible, but they are not. They contain pores that are filled with air. When subject to intense pressure, the pores are compressed, not the solid matter in the wood or cork itself. Low rate of diffusion. If a zinc plate and a copper plate are clamped together for a long time, a few atoms of each metal will diffuse into the other. This observation shows that diffusion does occur in solids. However, the rate of diffusion is millions of times faster in liquids than in solids. Second main idea. Crystal particles are arranged in a three-dimensional lattice. Crystalline solids exist either as single crystals or as groups of crystals fused together. The total three-dimensional arrangement of particles of a crystal is called a crystal structure. The arrangement of particles in the crystal can be represented by a coordinate system called a lattice. The smallest portion of a crystal lattice that still shows the three-dimensional pattern of the entire lattice is called a unit cell. A crystal and its unit cells can have any of one of 7 types of symmetry. This fact enables scientists to classify crystals by their shape. Diagrams and examples of each type of crystal symmetry are shown on the screen here.
Crystals are orderly arrangements of atoms. Crystals are distinguished by the forces that hold them together. Metallic crystals form when the valence electrons of the atoms move freely between nuclei. This sea of electrons is why metals such as gold and copper conduct electricity. Ionic crystals, such as these crystals of sodium chloride, rely on the attraction between the positive cation and the negative anion, which holds the crystal together. Molecular crystals form when the forces holding molecules together are the result of hydrogen bonding, dipole-dipole interactions, or London dispersion forces. Ice, the crystal form of water, is a good example of a substance that holds its crystalline shape due to a strong hydrogen bond. Covalent network crystals are crystals in which all the atoms are covalently bound to other atoms in the crystal. Diamond and silicon, which is used in making computer chips, are both examples of covalent network crystals.
Binding forces in crystals. Crystal structures can also be described in terms of the types of particles in the crystals and the types of chemical bonding between the particles. According to this method of classification, there are 4 types of crystals. These types are listed in figure 3.4 of your textbook or on the screen here. You will need to continually refer to this table as you continue through this section. 1. Ionic crystals. The ionic crystal structure consists of positive and negative ions arranged in a regular pattern. The ions can be monatomic or polyatomic. Generally, ionic crystals form when group 1 or group 2 metals combine with the group 16 or group 17 nonmetals, or nonmetallic polyatomic ions. The strong binding forces between the positive and negative ions in the crystal structure give the ionic crystals certain properties. For example, these crystals are hard and brittle, have high melting points, and are good insulators. 2. Covalent network crystals. In a covalent network crystal, Each atom covalently is bonded to its nearest neighboring atom. The covalent bonding extends through a network that includes a very large number of atoms. Three-dimensional covalent network solids include diamond and quartz, silicon carbide, and many other oxides of transition metals. Such solids are essentially giant molecules. The network solids are nearly always very hard and brittle. They have rather high melting points and are unusually non-conductors or semiconductors. Or should I say they are rather usually non-conductors or semiconductors. 3. Metallic crystals. The metallic crystal structure consists of metal cations surrounded by a sea of delocalized valence electrons. The electrons come from the metal atoms and belong to the crystal as a whole. This explains the high electrical conductivity of metals. 4. Covalent molecular crystals. The crystal structure of a covalent molecular substance consists of covalently bonded molecules held together by intermolecular forces, or IMFs. If the molecules are nonpolar, for example, hydrogen gas, which is H2, methane, which is CH4, or benzene, which is C6H6, then there are only weak London dispersion forces between molecules. In a polar covalent molecular crystal, molecules are held together by dispersion forces, again, London dispersion forces, and by somewhat stronger dipole-dipole forces, then even sometimes by the much stronger hydrogen bonding. For example, in water, which is H2O, and ammonia, which is NH3. The forces that hold polar or nonpolar molecules together in a structure are much weaker than the covalent chemical bonds between the atoms within each molecule. Covalent molecular crystals, thus, have low melting points. They are easily vaporized, they are relatively soft, and they are good insulators. Third main idea. The particles in amorphous solids are not arranged in a regular pattern. The word amorphous comes from the Greek for without shape. Unlike the atoms that form crystals, the atoms that make up amorphous solids, such as glasses and plastics, are not arranged in a regular pattern. Glasses are made by cooling certain molten materials in a way that prevents them from crystallizing. The properties of that result make glasses suitable for many uses, including windows, light bulbs, transformer cores, and optical fibers that carry telephone conversations. Plastics, which are another type of amorphous solid, are easily molded at high temperatures and pressures. They are used in many structural materials. Other, more recently created amorphous solids have been placed in many important applications. Amorphous semiconductors are used in electronic devices, including solar cells, copiers, laser printers, and flat panel displays for computer monitors and television screens.
When a substance changes from a liquid to a gas, the process is called vaporization. A liquid must absorb energy for vaporization to occur. Evaporation occurs when some molecules at the surface of a liquid move fast enough to escape into the surrounding air as vapor. Evaporation can occur well below a substance's boiling point. When a liquid is heated to its boiling point, molecules within the liquid absorb enough energy to form bubbles of gas within the liquid. When condensation occurs, a gas becomes a liquid. Condensation can be seen when water droplets form on the outside of a cold glass of lemonade. Water vapor molecules near the cold surface slow down enough to clump together on the glass, forming droplets.